Alright, ladies and gentlemen, I would like to thank you all for coming here today to listen to all our presentations. So what I'm here to talk to you today is essentially just how can I create a cheap and effective prosthetic that anybody could use in any kind of situation, but also return to them any sort of abilities to go into different areas and pick up different objects, say picking up a flower versus picking up a glass. So briefly, if you were born, a couple of 100 years ago, and you were born with a residual limb, or you lost your arm due to some sort of accident, you were quite unfortunate because very few solutions existed that afforded you the same mobility as a biological hand. So here we have what's basically the first hand that was made. It was made for a knight back in roughly around 1560. It had opening and closing, but it needed your opposite hand to operate it. Then we go on to like a Victorian era hand, which is just for more visual purposes. And then we have this hook here that is interchangeable, that you can put knives and forks on it. But again, it's very, very base level use, mostly just for aesthetic purposes. We then go on to now more modern day ones, which are purely mechanical body power prostheses. And when you wear them, it requires you to, say, move your shoulders to actually latch and unlatch the hand. But again, you have no control over it. It literally is just an open and close motion. In more modern day ones now, because it's actually quite a fascinating sector to be in, we have, as Mr. Frisbee had said, there's 3D printed hands available, and they do allow for a lot more customability and innovation within the sector. Another interesting area, I'm not sure if anyone's heard of, is like the B-Bionic model. It's been referred to as the Terminator hand. It's this one over here. It allows full articulation of the whole hand and the wrist. And then we also have now more modern hands which actually return the sense of touch to most wearers by implanting different sensors within the nervous system, and people can touch a surface with their biological hand and then touch it with the prosthetic hand, and still they can't tell any difference because they feel the exact same. So moving on towards my project. So the first thing is, you've probably seen I have various different pads stuck on me here. So I'm measuring what's referred to as EMG, or electromyography signals, on your arm. These are, of course, surface mounted because I wasn't allowed to use needles. So, what are EMGs? EMGs, as I said, are the signals that are measured from the surface. But these signals, where do they originate from? So, you think up on your head, I want to move my arm. There's neurons that travel down through your nervous system into your arm, and they create a chemical reaction, much like that in a battery. This chemical reaction can be measured using, like I said, the EMG signals. So what am I actually looking at? Within the arm, we have various different levels of muscles, and within those different levels, there's many, many more muscles. So if you can take your hand, you can even check this yourself. This is the posterior side, so we're looking at what's referred as the outside. In medical terms, it's referred to as the posterior. The muscle that I'm going to be looking at is the extensor carpi ulnaris. This, if you run your hand down the outside of the top of your arm and you flex it, you can actually feel that muscle. That is the strongest muscle on the outside of your arm, as it is used to extend your wrist. The other muscle that I'm using is on the anterior, or the bottom side of your arm. If you run your hand along again, the bottom of the hand, and you flex your hand like so, you can actually feel it. This is the flexor carpi radialis, and again, it is used in the flexion of the wrist. These are the most strongest muscles. They're also the most likely to be the residual muscles that are in either a post-amputation arm or someone who's born with a residual limb. IDS Kappa. IDS Kappa is a hospital in Kappa that produces and designs and develops and caters for individuals who wish to have prosthetics or orthotics. They cover all over the body, upper limb and lower limb, and they're the only place in Ireland that do so. So, of course, if I want to build a prosthetic, where's the first place you go? You go to the people who know what they're talking about, and the people who have round experience, and also patients that can tell you what you want. There's no point in me designing an arm that nobody wants to use, or that's not going to be of any benefit to anybody possibly using it. So I got hooked up to all their machines. As you can see here, we have a technician checking my arms out. And again, the muscles that I discussed, the posterior and the anterior, the outside and the inside, these muscles were pointed out to me that these are the most commonly used ones within industry for the exact same reasons I had mentioned, and also research myself. After they found the most ideal point on those muscles, then I got connected up to their system here, and if you can see, I'm not sure in the back if you can, but we can actually monitor different signals. Along here, this is one of the original kind of analog versions of checking the signals, and depending on how strong the muscle is, so how much power you put into flexing it, depends on how high up these LEDs raise, and the different colours correspond with a different size. An interesting thing that I learned when I was out there was, if anyone has ever played Flappy Birds, they had a game that I had to play on the computer. They use it in regards to training people before they get their arms. You have to control, by the strength of your muscle, the height of the cursor. Now at the time I had to control 2 different cursors going through different gates, and I can tell you, as an able-bodied person with extremely strong muscles in my arm, it was very, very difficult to do, and I couldn't imagine having to spend a lot of time training in this field. So I wanted to develop something that would allow me to put a system on an arm, or develop a new arm with my system that somebody could easily take up and use, and it's almost intuitive. So first we'll go into the circuit. The circuitry is broken down into 2 parts, instrumentation and control. So instrumentation circuit. So I won't go into a lot of the detail because I'm not sure how many people have actually backgrounds, and I might bore you with the technical side of it. So essentially it's broken down into 4 parts. The in-amp, which takes the signal directly from the arm and is passed in. The signal I'll receive looks like this. So it oscillates quite a lot, but this is on a very small level, and it's too small for the microcontroller that I'm using to actually see the differences between flexing and relaxing, and as a result I need to amplify it. So the next stage is passed through to is the op-amp. The op-amp again just simply steps it up. So we were originally working in the millivolt range, now we're working within full voltage, so the differences are quite large now. The next stage though that we pass it through, because as I said, it oscillates quite a lot, and using the computers, although computers are quite smart, they're quite dumb. They can only see the data that you present to them. If you're presenting an oscillating piece of data and I want a very streamlined and conditioned signal that, you know, to operate the code, this won't give me any output that I wanted. So then I used an envelope detector. So the envelope detector then in turn gives me this nice clean red signal. So as it goes up, it's to come back down, but it's in one straight line. So now I have a solid signal to work with. But again, digital or analog signals are very hard to work with, and if I am to put this into code, I have to, you know, calibrate it for different people. So what I've done then is I've inputted a comparator which sets this green line, which can be calibrated to the wearer, and then as a result it outputs this purple line, so you either see an on or an off signal, and that's the circuit. So we have the instrumentation amplifier, we have our gain amplifier, we have our envelope detector, and our controller. So the control circuit looks like this, lots of fancy wires and pretty colours, and then this is the 2 on the board. So our control circuit here and our instrumentation circuit here. How the code works, which is the real kind of base on the innovation here, is how the people interact, what they want versus their output, is this. So we have, remember I said there was a posterior and an anterior, so we refer to them as a posterior flexion and an anterior flexion, and when you tense both, that's called a code contraction. So in the standby state, you code contract, you then go into a state referred to as grip set. Within the grip set, depending on what way you flex your arm, you can then actually select a level of grip that you want. So depending on what force you want to apply or what object you want to move or lift, you can then select that. Once you've done so, again, another code contraction will change your state. You will then go into the closing state, which will operate in a mechanism that I've designed, which will tighten the hand to a preset value correlating with the state you selected. Once closed, you'll get a green light to go. You can move about and pick your object up and down. We also have fail-safes introduced in case someone has selected the wrong value or quickly needs to release it while it's being closed. After it's been closed and you've finished doing what you need to do, another code contraction then will return you to the standby state and release it. But say for argument's sake, I'm picking this glass up and I have to keep moving it over and back. Do I have to go back through all of this here? No. I've introduced another line here whereby in the standby state, executing another code contraction that lasts longer than 3 seconds will allow you to skip this process and go straight to closing, thus speeding up any process that someone might need to execute. So the mechanics. I'm not a mechanical engineer, so I had lots of fun learning how to use SolidWorks and implementing some of these different designs. So as you can see here, I used the ratchet and pawl system for tightening the mechanism. Also, this was used as an energy saving, so as to reduce any strain on the motors having to retain and hold the hand in the position. And then again, like Occam's razor, the simplest solution is the best solution. I didn't want to be using loads of motors in the hand, so I wanted to just use 1 or 2 motors to control the pulling in. And the hand actually has no motors in it. It's all done with just some conduit, flexible conduit and cables, which you can refer to as tendons, pulled down tightly into a bell crank here, and then as it tightens, so does the hand. Lastly, I'd also like to say, I have also been blogging throughout the whole process on my WordPress, so that's the account there if anyone wants to go on and have a further read. You can pop on over, there's multiple different tabs on different projects that I've done. You can head on over to the DT009 Finding Your Project, and the drop down menu, it's tabulated in such a way that depending on what you're interested in and what you want to find out, it's all up there. So I know they said no questions, so I won't ask for any, and I'll thank you for your time.